For more than 2 decades, Saturn appeared to be doing something that, according to basic physics, planets simply are not supposed to do. Its measured rotation rate kept changing, drifting up and down over the years, as if the sixth planet from the Sun were somehow speeding up and slowing down its own spin on a whim. Planets do not do this. A world's rotation, once established during its formation billions of years ago, should remain essentially fixed for the rest of its existence, barring some catastrophic external event. And yet, dating back to observations made by NASA's Cassini spacecraft in 2004, Saturn's numbers kept refusing to cooperate. In May 2026, using observations gathered by the James Webb Space Telescope, a team of researchers finally closed the loop on this decades-long puzzle, tracing the entire strange phenomenon back to something genuinely unexpected: a self-sustaining, planet-wide engine powered by Saturn's own northern lights, quietly generating the very winds and electrical currents that had been confusing scientists' measurements the whole time. This is the real story of how James Webb finally revealed Saturn like never before, not through a single striking photograph, but through years of painstaking, coordinated observation that solved one of the ringed planet's oldest, strangest mysteries and produced, along the way, the most comprehensive combined view of Saturn's atmosphere ever assembled. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why Saturn's apparent rotation problem genuinely puzzled scientists for so long, you first need to understand why measuring a gas giant's rotation rate is such a fundamentally different challenge than measuring the rotation of a solid, rocky planet like Earth or Mars. Saturn has no solid surface to track. It's an enormous ball of hydrogen and helium gas, with cloud bands visibly drifting and shifting at different speeds depending on latitude, meaning you can't simply watch a fixed surface feature complete one lap and call that the planet's true rotation period. Astronomers instead have to rely on an indirect method, tracking periodic radio signals generated deep within the planet's interior, signals tied to Saturn's rotating magnetic field, since that magnetic field is assumed to be anchored to the planet's actual interior rotation, providing a reliable proxy for the true spin rate hidden beneath the visible clouds. The problem is that this proxy measurement stopped behaving reliably. Cassini's own observations, beginning in 2004, found that Saturn's calculated rotation period, based on these magnetic and radio signals, appeared to be gradually drifting, changing by minutes over the course of the mission, a result that made no physical sense if the planet's actual interior rotation was genuinely stable, which every reasonable model of planetary physics said it should be. Scientists spent years trying to understand what was actually going on. The first real breakthrough came in 2021, when a team led by Professor Tom Stallard of Northumbria University proposed a genuinely clever reinterpretation of the entire problem. Saturn's rotation, Stallard's team argued, wasn't actually changing at all. What was changing were the electrical signals tied to Saturn's aurora, its own version of the northern and southern lights, and those signals were being influenced by winds blowing through Saturn's upper atmosphere, winds capable of subtly distorting the very electrical measurements astronomers had been using as their proxy for the planet's rotation. In other words, the planet had been stable the entire time. The measuring instrument, in a sense, had been quietly lying to everyone, thrown off not by Saturn's actual spin, but by an entirely separate atmospheric process nobody had properly accounted for. That 2021 finding resolved the most confusing, most physically troubling part of the puzzle, the apparent violation of basic planetary physics, but it immediately opened up a second equally important question that remained genuinely unanswered for years afterward. If atmospheric winds were responsible for throwing off the measurements, what was actually driving those winds in the first place? Winds don't simply appear from nothing. Something has to be generating the energy that sets them in motion, and identifying that underlying driver required a level of atmospheric detail that no instrument available in 2021 could actually provide. That's precisely the gap James Webb was uniquely positioned to fill. Stallard and a genuinely large, multi-institutional team of collaborators, drawing on researchers from Northumbria University, Boston University, the University of Leicester, Aberystwyth University, the University of Reading, Imperial College London, Lancaster University, and the Johns Hopkins University Applied Physics Laboratory, turned Webb's instruments towards Saturn's northern auroral region and observed it continuously for an entire Saturnian day, a sustained, unbroken observation window that gave the team a level of detail no previous instrument had ever achieved for this specific region of the planet. The team focused their observation on a specific kind of infrared light, emitted by a molecule called trihydrogen cation, which forms naturally in Saturn's upper atmosphere and functions as a genuinely useful, direct indicator of local temperature. By carefully mapping exactly how the glow from this molecule varied across Saturn's auroral region, the team produced the most detailed temperature and charged particle density maps ever assembled for this part of the planet. The improvement in precision compared to earlier instruments was genuinely dramatic. Earlier measurement techniques carried uncertainties of roughly 50 degrees Celsius, an error margin large enough to completely obscure any subtle, localized temperature variation. Webb's observations, by contrast, achieved roughly 10 times that precision, finally allowing researchers to identify specific, localized patterns of heating and cooling across the auroral region for the first time in the history of Saturn observation. What that newly precise data revealed, once compared against theoretical models that had actually been developed more than a decade earlier, was a genuine, satisfying confirmation of a mechanism that had been proposed but never actually verified. Those older models had predicted that the atmospheric heating responsible for driving Saturn's mysterious winds would only make physical sense if the heat source were located in one very specific place, precisely where the most energetic auroral particles actually enter Saturn's atmosphere. Webb's new, high-precision maps confirmed exactly that. The heating wasn't happening randomly or diffusely across the auroral region. It was concentrated exactly where theoretical models had predicted, tightly correlated with the specific location where the aurora's own particle bombardment strikes the upper atmosphere. Putting the full picture together, the research team described a genuinely elegant, self-sustaining physical cycle, a real planetary engine quietly running underneath Saturn's dazzling polar light shows. Energy deposited into the atmosphere by the aurora heats specific, localized regions. That concentrated heating generates winds. Those winds, moving through Saturn's magnetized upper atmosphere, generate electrical currents. And those currents, in turn, help power the aurora itself, continuing to heat the atmosphere and sustaining the entire cycle indefinitely, an ongoing feedback loop with no obvious external trigger required to keep it running. Stallard's own description of this mechanism captures the elegance of the underlying physics, about as clearly as any technical explanation could. What we are seeing, he explained, is essentially a planetary heat pump. Saturn's aurora heats its atmosphere, the atmosphere drives winds, the winds produce currents that power the aurora, and so it goes on. The system feeds itself. He went on to describe the genuine multi-decade arc of the underlying scientific investigation directly. For decades, he said, researchers knew something strange was happening with Saturn's apparent rotation rate, but couldn't explain it. The team then showed it was being driven by atmospheric winds, but still didn't know why those winds existed in the first place. These new observations, he explained, made possible specifically by Webb, finally gave the team the evidence needed to close that loop entirely, connecting cause and effect across a mystery that had persisted for more than 20 years. It's worth appreciating exactly how significant this finding is beyond simply resolving one planet's specific measurement puzzle, because the research team has been direct about its broader implications. The study found genuine, direct evidence that Saturn's atmosphere and its magnetosphere, the vast surrounding region of space shaped by the planet's magnetic field, are far more tightly interconnected than scientists had previously appreciated. Activity happening within the atmosphere appears to directly influence conditions out in the magnetosphere, while the magnetosphere simultaneously feeds energy back down into the atmosphere. An ongoing two-way exchange that likely explains why this entire self-sustaining cycle has remained so stable for so long. Staller connected this finding to a much broader scientific principle, one extending well beyond Saturn specifically. This result, he said, changes how researchers think about planetary atmospheres more generally. If a planet's atmospheric conditions can genuinely drive electrical currents out into the surrounding space environment, he explained, then understanding what's happening deep within the stratospheres of other worlds, including planets throughout our own solar system and potentially exoplanets orbiting other stars entirely, may reveal interactions between atmosphere and magnetosphere that scientists haven't even considered yet. This spin mystery breakthrough, published in the peer-reviewed Journal of Geophysical Research, Space Physics in May 2026, arrived as part of a broader, sustained campaign of Webb-based Saturn observation that had already produced something else genuinely significant just 2 months earlier. In March 2026, NASA and the European Space Agency jointly released what they described directly as the most comprehensive view of Saturn to date, a coordinated pairing of images gathered by both James Webb and the Hubble Space Telescope, observing the planet through two fundamentally different, complementary wavelengths of light. Hubble's contribution came from its long-running Outer Planet Atmospheres Legacy program, known as OPAL, an ongoing observational campaign that has spent more than a decade patiently building up a detailed record of how the outer planet's atmospheres evolve and change over time. Hubble captured its portion of this particular Saturn observation on August 22, 2024, working in visible light, the same general range of wavelengths your own eyes can perceive, revealing Saturn's softly banded atmospheric structure and its iconic, brilliant ring system, along with several of the planet's moons visible in the same frame, including Janus, Mimas, and Epimetheus. Roughly 14 weeks later, on November 29, 2024, James Webb captured its own complementary observation of the same planet, this time using its near-infrared camera, working in wavelengths of light entirely invisible to human eyes, but capable of revealing atmospheric structure and chemistry that visible light alone simply cannot access. The scientific value of pairing these two specific observations together comes down to exactly what each instrument is uniquely capable of detecting. Both telescopes are ultimately sensing sunlight reflecting off Saturn's banded clouds and atmospheric hazes, but they're doing so in genuinely different ways. Hubble's visible light observations excel at revealing subtle color variations across the planet's visible cloud tops, differences in atmospheric chemistry and particle composition that show up as genuine, if often subtle, shifts in hue. Webb's infrared observations, by contrast, are sensitive to clouds and chemical compounds sitting at many different depths simultaneously, from Saturn's deep, dense cloud layers all the way up to its much thinner, more tenuous upper atmosphere. Combining these two complementary views effectively allows scientists to slice through Saturn's atmosphere at multiple altitudes at once, examining the planet layer by layer the way you might peel back the layers of an onion to examine its internal structure, rather than being limited to a single, flattened view of whatever happens to be visible from the outside. Webb's specific infrared observations revealed several genuinely striking details that simply aren't visible in ordinary visible light. Because Saturn's rings are composed primarily of water ice particles, which reflect infrared light with exceptional efficiency, Webb's image showed the ring system appearing exceptionally bright, dramatically more prominent in infrared than in visible light. The infrared observations also revealed Saturn's atmosphere in genuinely unprecedented detail, showing distinct cloud bands and subtle variations tied to temperature fluctuations, wind patterns, and other underlying atmospheric dynamics. Within these observations, Webb captured a long-lived persistent jet stream researchers have nicknamed the ribbon wave, a feature, meandering across Saturn's northern mid-latitudes, its exact path and structure shaped by otherwise undetectable atmospheric waves rippling through the planet's deeper cloud layers. The combined images also captured something genuinely nostalgic and scientifically valuable at the same time, a faint but clearly present view of Saturn's famous hexagonal jet stream, the strange, geometrically precise, six-sided weather pattern encircling the planet's north pole. First discovered by NASA's Voyager spacecraft back in 1981, and remarkably persistently stable in the more than 4 decades since. According to researchers involved in the observation, these new Webb and Hubble images may represent some of the last high-resolution views of this iconic hexagon available until the 2040s, since Saturn's slow 7-year seasonal cycle means the northern hexagon region is now heading into a prolonged period of winter darkness that will keep it hidden from clear observation for years to come. Also visible within Webb's infrared data was a distinct gray-green glow near Saturn's poles, most likely connected to high-altitude atmospheric aerosols or auroral activity, potentially generated by charged particles interacting with the planet's magnetic field, offering researchers yet another genuine clue about the physical processes shaping Saturn's uppermost atmosphere. The same broad region of the planet that the spin mystery research would go on to study in even greater detail just months later. It's worth understanding why this particular window in Saturn's long seasonal cycle made these specific 2024 observations so valuable, beyond simply being a convenient moment for 2 major space telescopes to both point in the planet's direction. Saturn experiences seasons in a genuinely dramatic way, driven by its axial tilt combined with its enormous, roughly 29-year orbital period around the Sun, meaning each individual Saturnian season lasts, on average, around 7 Earth years. The observations captured by Hubble and Webb in August and November of 2024 caught the planet in the specific act of transitioning from northern summer toward its 2025 equinox, the point where the Sun sits directly above Saturn's equator, illuminating both hemispheres equally, before the planet continues its slow seasonal march toward southern spring, and eventually, sometime in the 2030s, southern summer. As that transition continues to unfold in the years ahead, researchers expect Hubble and Webb to gradually gain progressively better, clearer views of Saturn's southern hemisphere, a region that has remained comparatively difficult to study in detail throughout the planet's long northern summer phase. This ongoing observational campaign fits into a much broader, sustained pattern of Webb-based research into Saturn and its surrounding system that has continued producing genuine scientific value across multiple separate studies. In February 2025, using Webb's own imaging capabilities, a research team led by Mariame El-Mutamid successfully identified a brand new moon orbiting Uranus, formally designated ESA 2025 U1, a small object roughly 8 to 10 kilometers across, becoming the 29th confirmed moon in the Uranian system. A reminder that Webb's infrared sensitivity continues turning up genuinely new discoveries throughout the outer solar system, not just around Saturn specifically. Webb has also continued contributing to a broader, ongoing research effort studying the atmospheres of gas giant exoplanets orbiting other stars entirely, work that draws directly on the same fundamental atmospheric physics techniques being refined through. Also visible within Webb's infrared data was a distinct gray-green glow near Saturn's poles, most likely connected to high-altitude atmospheric aerosols or auroral activity, potentially generated by charged particles interacting with the planet's magnetic field, offering researchers yet another genuine clue about the physical processes shaping Saturn's uppermost atmosphere, the same broad region of the planet that the spin mystery research would go on to study in even greater detail just months later. It's worth understanding why this particular window in Saturn's long seasonal cycle made the specific 2024 observations so valuable, beyond simply being a convenient moment for two major space telescopes to both point in the planet's direction. Saturn experiences seasons in a genuinely dramatic way, driven by its axial tilt combined with its enormous, roughly 29-year orbital period around the Sun, meaning each individual Saturnian season lasts, on average, around 7 Earth years. The observations captured by Hubble and Webb in August and November of 2024 caught the planet in the specific act of transitioning from northern summer toward its 2025 equinox, the point where the Sun sits directly above Saturn's equator, illuminating both hemispheres equally, before the planet continues its slow seasonal march toward southern spring, and eventually, sometime in the 2030s, southern summer. As that transition continues to unfold in the years ahead, researchers expect Hubble and Webb to gradually gain progressively better, clearer views of Saturn's southern hemisphere, a region that has remained comparatively difficult to study in detail throughout the planet's long northern summer phase. This ongoing observational campaign fits into a much broader, sustained pattern of Webb-based research into Saturn and its surrounding system that has continued producing genuine scientific value across multiple separate studies. In February 2025, using Webb's own imaging capabilities, a research team led by Mariame El-Mutamid successfully identified a brand new moon orbiting Uranus, formally designated ESA 2025 U1, a small object roughly 8 to 10 kilometers across, becoming the 29th confirmed moon in the Uranian system. A reminder that Webb's infrared sensitivity continues turning up genuinely new discoveries throughout the outer solar system, not just around Saturn specifically. Webb has also continued contributing to a broader, ongoing research effort studying the atmospheres of gas giant exoplanets orbiting other stars entirely, work that draws directly on the same fundamental atmospheric physics techniques being refined through.